workshop, we have a couple of notebooks where we're just going to see implementations of logistic regression, which is something I mentioned earlier. It's kind of something you can use for classifying images, for example. Linear regression for making predictions, and neural networks, which is like deep learning and probably the most interesting part of machine learning. I mentioned this already, logistic regression. The problem we're going to look at is we're going to have a training set, which is just a bunch of pictures. Once we've messed around with the data, they're kind of no longer pictures, they're arrays of RGB values that have been flattened, because that's the way you can feed them into your program. If you imagine, like, you can't really just give a Python program a picture and go, like, figure that out. You've got to do something to the data first. And what you do is you separate the RGB values into a matrix. You kind of flatten it out. You add labels to the data, to the training data. And what training data is just a set of data where you know the answer. That's supervised learning. It's data that you know what it is. Each picture will have an image. It'll say, I'm a cat, I'm not a cat. And if you give the machine enough of these pictures, it'll start to build up an idea of what pictures contain cats and what pictures don't. You also use what you call a test set. So if you imagine you train your machine with training data, but you want to verify the data is actually working, so you have a separate test set which has images that are also labeled. You know the answers to them, but they weren't part of the training set. And then you can test the accuracy of your learning algorithm based on that test set. So it's kind of simple enough so far, right? The concepts at least. And logistic regression is a really kind of a simple one because it's usually like a yes or no answer at the end of it. They get a lot more complicated than that, but this is a good one to get the concepts. And then we'll take a look at prediction. We're not going to use the housing price prediction problem. We're going to use this small data set, which is like, it's American party growth based on presidential terms. So you got like Republicans, Democrats, how much they've grown based on who was in power historically, and we're going to try to predict how much each party is going to grow in the next term. And then we're going to start looking at neural networks. This representation here is an example of a neuron. Neural networks are based loosely on how we think the human brain is designed, which is a set of neurons that can take information and do something to it and put something else out. So what you can imagine here is that you've got essentially a vector of data. You put it into a neuron, you apply some function to it, and then you get something out. And usually what you get out is what we call like a prediction. So you take some data in, you decide, you give it a weight. So you say, how important is this data? You multiply that data by that weight, essentially, and you apply, like in the case of logistic regression, you apply a linear function to what's coming out. We're using a sigmoid in this case, which will make it a logistic, as in it'll turn it into a true or false. Or you might send it out as like a probability or some other value, depending on your domain, what your use case is. Sorry, Derek, I was just going through the things there, but you didn't miss much. So, and then your output is that value, whatever it is. And a neural network, which I'm going to jump onto, is a combination of these things. So you imagine you've got some way that you can have many different kinds of neurons in there. You can combine them. You can have like one input with many outputs. You can have many inputs with one output. You can have many inputs and many outputs. Again, it all depends on what you want to do. The design of your neural network entirely depends on your use case, obviously. What kind of data you want to come in, the shape of your data. When we say shape of the data, think of as essentially how much data you want to process at once. How many columns and rows there are in your matrix is the shape of data. And to kind of explain take the case of an image, right? So if the shape of the data of an image is going to be the entire image. And the reason for that is, like, imagine if you sent in a pixel, or you sent in pixels one by one into a neuron, for example, what would it be able to derive from that? Nothing. And if you imagine what would a human be able to derive from one pixel coming into a system, or into your vision? Nothing. You have to pass in as much data once as, like, for example, a human might need to identify something. And that'll become more clear when we start looking at a bit of code and stuff in it, what I mean by that. And then the really kind of cool part, it doesn't look very cool there, but the cool part about deep learning and how it works is this forward and backward propagation. And what that means is, like, forward propagation is when you feed the data in and it goes through your neural network and your system generates some predictions, and then you compare it against what you expect the outputs to be, as in the correct labels. You figure out how wrong you were. You adjust your weights, which we'll talk about in a minute, to try and kind of bring it more in line with what would be a better prediction. And then you send that backward, propagate that through your system for it to learn, and you iterate on that. And that's fundamentally how deep learning works. So the end part, once you've forward propagated, discovered how wrong you are, you start doing a thing, mostly what people use is a thing called gradient descent, which is you're trying to optimize your predictions. And then you send what you learned from doing that back through the system, you memorize that essentially, and send it back again, and it's this iterative cycle. And if you have enough data, and if you keep training your system enough, it'll eventually become so accurate that, you know, it's useful. And that's sort of how so many systems are working out there today. They're just keeping fed data, they're constantly optimizing. All the people that work, you know, data scientists working in machine learning spend their whole time figuring out algorithms to optimize the error detection and better algorithms in this system. But this is fundamentally how it works. Think next, more simply, predict, compare, learn is the 3 steps you can think of in a system. Make a prediction, compare how that prediction performed against real outputs, and then learn from that. No, we're not taking a break. We're looking at, we're going to look at some workbooks. They're called notebooks. I keep calling them workbooks. The notebooks, I mean. So the first one, I'm not going to quite do them in the order I mentioned there. I'm going to start with linear regression. And this is just me, I'm just going to show you this. You know, you don't have to do anything here. But the next one is going to be a practical exercise, and you're going to be doing a lot of stuff in the next one. But this one I'm just going to show you. You can follow along with me if you like. Can everyone see this okay? A little more. The first thing there, in case you're wondering, if you put a not in front of the thing there, it basically runs that command on the system. And what I'm doing there is I'm just removing this TF linear regression directory. And what that is we're actually going to use TensorFlow a bit here. We won't talk too much about TensorFlow yet, but I'm just going to show you like 1 or 2 cool features of it while we're doing this. And TensorFlow will build a model when we're training it, and it's going to put it into that directory. So I'm just removing the model in case you've run it already. We just have a very simple CSV file in here. I mentioned it already. So in that CSV file, we just have 3 columns. We have term, parity, and growth. And then we're just going to use that data set to do a linear regression and try to predict growth for each parity. Here I'm just demonstrating some very simple use of other libraries that aren't TensorFlow or that aren't just plain Python either. Just things that you'll come across all the time. Just a way for us to read in the data with pandas. But that we're just going to use NumPy. I'm going to talk about NumPy a lot, but I won't go into it just yet. But NumPy is just a way of really making your life a lot easier when you're working with matrices and vectors. We're just initializing with some variables here. And then we're using sklearn, which is another popular data science library, to do a linear regression. It's like super simple. Don't worry too much about the details. We're just saying, here, build me a linear regression model with this data and predict the growth for, I think it's Republicans and Democrats, and just show me the prediction. So it just takes the data in, runs a linear regression function on it, and gives you back the predictions. Very simple. But you can imagine like that you can apply that to various other kind of data sets. And like in this case, we only have like 3 columns, but you can imagine scenarios where you have hundreds of columns based on anything. And I just ended a quick glimpse at TensorFlow before we go away from it and back to it again. But this is the very same thing in TensorFlow. A lot of code there. I don't want to go into it too much, but or just think that it's kind of doing the same thing as above. I had to mangle it a little bit for it to work, to look similar to the code above. But the extra thing that you get for writing all that kind of messy looking code is you get a persisted model, which we didn't get in sklearn above. And you also get a way to go in and debug and view how a model is being built. So if you like, yeah, when we're building a model, we're kind of building a graph of operations so that whenever we feed new data in, it'll go to that graph and go to the thing I mentioned where it'll like predict something, it'll, optimize it, and it'll feed it back and persist it into our model. And you can see down here, if you're able to open up a console in this directory, let's do it from and it's probably not very visible there, but if you paste the command that I had in the workbook, and you're in the workbooks directory, you get this, it should just work that you can go to localhost 6006 or whatever, but for some reason I tried this earlier and it didn't work, but this works. I have no idea why. So what we did is we started up a thing that TensorFlow has called TensorBoard. And we won't use it again today, but it's something to keep in mind. It's like the handiest thing ever. It shows you a lot of cool stuff. It shows you like how many steps it took before we reached the optimal learning rate there. That's the kind of, the loss is like, at the start it was like, you were this wrong, and now you're this wrong, and now you're this wrong, and eventually we're doing our gradient descent to get the loss down to, you know, trying to get it down to 0. Very hard to get it to 0, but somewhere near 0 is usually good enough. And TensorFlow also visualizes the graph that it builds. So it's not very obvious in the code what the graph looks like, but it's good to be able to visualize the graph of operations that are going on in there. And like if this stuff doesn't, if you like really don't know what the hell this stuff is or what's going on, don't worry too much. I just wanted to kind of expose you to it for a minute, just so you know it's there. Deep learning work notebook. Introduction to deep learning. Everybody there?
Yes.
Good. Neil is in it.
No, go to your Jupyter notebooks. Go back to the GUI. Or you go to just leave it open. And then you can go to
Everybody good? Alright. So earlier on I showed a picture of a neuron, which is something that takes data in, runs some function on that data, and gives you a prediction. And this is, as I mentioned here, probably the most basic and completely useless neural network possible. It's a function that takes in a weight, and I'll talk a lot about weight in a minute. It and it takes the input and a weight, and it multiplies the input by the weight, and that constitutes prediction. So here we're saying, based on the given weight, we're able to derive something about the input. And make a prediction on that.
Deep learning. Oh, yeah, from GitHub people. Oh, from
Just from that.
Bitbucket?
Yeah.
Oh, pull it from GitHub. I don't even use Bitbucket.
You're missing the deep learning one, is it?
The deep learning file is not in Bitbucket, but it's in GitHub.
It's not in Bitbucket.
Yeah, you might not have pushed it.
Oh, it's there. It is, yeah. It was only today I pushed it.
Also, that's it.
I wrote this, I wrote this last night.
Before today.
I did this morning.
Maybe
now
you
you're on
need
Wi-Fi.
it.
Use GitHub.
That's it.
Yeah, it's too cool. And if you want, just you commit what you have and pull down, or you get a conflict. Anyway, I'll just start talking while anyone's resolving their Git issues. But I talked about neural networks to kind of help us understand a little bit about how the neural network works with the predict, compare, and learn pattern. I just created this arbitrary problem for us to solve, and I don't like soccer at all, but my kid has gone mad into it, so I'm trying to pretend that I like it. So I came up with the penalty score problem, and the problem we're going to look at is kind of I guess it's inspired a little bit from FIFA or something, but where we have some information about a player and we have some information about a goalkeeper, and we're going to try and predict the likelihood of the player scoring a penalty on that goalkeeper based on those attributes. Now there's loads of little things you'll probably, once you start looking at it, you'll be like, that's not enough data to predict that, or we're not taking in the wind or the location. And that's totally true, it's totally valid, and that's the whole big thing about machine learning, is you're always trying to figure out what more information you need to make this prediction better. But right now we're going to go with what we have, and we're going to build a neural network with that data and see how we get on. So there's a lot of text here. This is like if you go back reading over it, we don't have to read it right now, but I just explain the problem as I just did. So things to think about when you're looking at the code. How do we know if our prediction is correct? Well, in this case, we have some training data. We're not going to use test data. You would use test data usually afterwards, after you've trained the model, you test it and go back again. But right now, we're just going to use some training data. So we actually know the answers already, and we're just going to try and make this thing repeat the answers that we know already, basically. What do we change to arrive at the correct result? We change the weight. So the way to think about this, and I should have made a visualization for this, but I didn't get around to it, is that each neuron in your neural net is kind of something, it's almost like a dial, right? And like as different features, they're called, right? And you can just think of these as columns in the data set, but different features come in. Each of these features has a weight associated with it, like the importance, how much it affects the machine's knowledge. So the weight of the knowledge, and like as you build up knowledge, you understand more about how different things affects the end result. So you're training your neural net to dial these knobs, which weights. So in this case, we have, if you like, a list of all the attributes, the keeper and the player, and for each attribute we have a weight, and our machine is going to go in and we're going to tweak the weights until the machine gets all the weights just right, so that it's predicting exactly as we want it to. So basically, our job is to get the weights right, and once you have the weights right, the system has learned. It has learned with the knowledge that we had, it learns what the weights are. And actually, for our first step, we're going to be the ones tweaking the weights manually, and we're going to do that now. So I'm just defining two buckets of data. We've got a player, and again, don't take this data too seriously. I don't know anything about soccer. I just made this up. Feel free to change it, right? But if you think these are the wrong attributes, you're right. I mean, I have no idea. This is our training data. It's an incredibly small amount of data, but just so we can actually see it. This is our training data. This function here, all it does is it basically flattens out that data, but I'm just doing it in a way that's kind of very easy to visualize here. We're taking that data in, and like each array of data is going to have all the attributes. The array the vector we call them, and its features, we don't distinguish in there like this is player, this is keeper. All we're doing is we're flattening that data and we're applying weights to each feature. And like what determines whether or not a player is likely to score, the probability, is the weights that we put on each of those features. So we're not thinking about objects, we're not thinking about a domain or anything, we're just applying volumes, weights to the data points that we have. And then this training set, the thing on the far right here is the expected output. This is the expected, so you can imagine somehow that we know somehow historically that this player scores against this keeper 0.7 with a 0.7 probability in general, and based on both their attributes, we've come up with that probability as being the correct probability for this scenario. And obviously the goal is that we will eventually want to feed the system this data without the answer, and we want it to give us back the correct answer, or at least something that's almost correct. So as I mentioned, we're just flattening out the training data. We're creating a list of expected outputs, and we just print them out here. And then we just have a little warm-up exercise. Get the coding skills going. Oh crap! Never mind. I accidentally left the answer in there. That's not a warm-up. So you all got it. But the next one is good. Alright, so basically all I wanted to do there was there's this weighted sum function. I just wanted you to have a look and just see how you'd implement that. And basically all it was, and this is such a common operation when you're working with matrices in machine learning, it's called the dot product, but in this case we're just keeping it simple, calling it a weighted sum, where you multiply all the things on the left with all the things on the right, and you sum it up in the end. And I'm rounding it here just to make it nicer to look at. That's the only reason. There's no actually good reason to round it besides visual. The next one I didn't accidentally leave in there. So now we want to build a neural network. And your job is to try and implement this. I have a hint in there that it can be done with one line. So what is the neural network? It takes your inputs, takes the weights, in this case. Like the hint is in the function that we implemented. So like you probably think like one input, one weight, but in this case we happen to have a list of input and a list of weights, which is almost always the case. You hardly ever have one input and one weight. And we're just creating a prediction out of that. And does anyone remember how you create a prediction using an input and a weight? You multiply them. So have a go off and see how you get on, and let me know if you get an answer. I'll have to limit this to about 4 minutes or something. That's the simplest neural network that we can build right now. So we're just taking the inputs and multiplying them against the weights. Yeah, and the important thing is that the inputs is the same size as the weights. And the inputs here are the attributes of the player. So for example, power, and we were saying that the corresponding weight for the power and then the corresponding weight for accuracy, each thing has a weight associated with it. And the way the prediction works is we multiply the value by its weight, and that produces a prediction. And in this case, we're producing, we're doing a dot product of those two things and coming up with a single value there, which is the probability of the player scoring the penalty. Still pretty abstract, I know, but we'll go more into detail about it now. Alright, so figure out the weights. This one doesn't require any kind of coding stuff. It's just fiddling around with numbers. So we have the training data, and we have a neural network. I know it's a bit of a stretch to call it a neural network. It's a really simple function, but it's a very simple neural network. Now we want to figure out what the weights are. And in the next block of code, I've just assigned some weights there. I've started them to 0. I've filled in 1 for you, which I know to be correct on the expected output, right? So this is to get you to the point where it matches the training data expected results. And your challenge is to see, can you tweak these weights so that when you run this code, I'll run it now, that the expected predictions and predictions match. So like obviously right now they don't. And it's just to fiddle around with the weights for a bit and see if you can figure out what the correct weights are. And I'm not going to leave much time to this, just I'm going to say like 3 minutes.
Machine learning algorithm to integrate with machine learning.
This is human learning.
Exactly. I'll stop it there. But the point of that exercise is to show you how annoying that would be to do if you had to do it manually. But I'll show you the right answers anyway, just for completeness. There is somewhere. There we go. Just to prove that it can work. Okay, so actually, just if you want to see the value, or if you wanted to see them, come back. There I was. Pretty, you know. Those are the ways that get you those answers, basically. So that, what we just kind of looked at was. Oh yeah, and just another thing that you often see is just the overall accuracy of the predictions at this point, which is 100%, or an error rate of 0, if you like. I'd said I'd come back to this library called NumPy. So you saw the way that we had to implement a weighted sum function, and we had to do stuff like flatten the data ourselves and all that. NumPy is a data science numerical library that does all these things for you. So if you could harken back to college days where you might have done some of this stuff, like doing matrix operations and all that, NumPy has all that kind of notation or whatever that you'd be familiar with. And then this is the example of the above code just using NumPy instead. So we're just doing the dot on the two matrices, or the two NumPy arrays, they're vectors. So instead of doing a weighted sum on it, and then we're looping over the input data set there, and just coming up with our predictions in there, using NumPy instead. And you'll generally use NumPy like all the time when you're working in machine learning. It just saves you a lot of hassle instead of having to do loops, maps, filters, all that kind of stuff on lists. Use NumPy. So it's worth looking into, and we're reading up a bit on that. Just show it's still working. So remember before I mentioned predict, compare, learn as being the fundamental steps. What we did just there was the predict step, and we tried to do the compare and learn ones manually. Obviously that sucked. So the next thing we're going to look at is how to make a machine do it for us. And what we're doing, what the machine does is it tries to, once it's got a prediction and you've got your expected outputs, we're trying to figure out like the magnitude of error at the point where we made our prediction versus what the right answer should have been, and we're trying to tweak the weights that we put them up or down based on how wrong we were, and then send it back and redo it again, and keep doing it until everything, like all of the data, gets to a higher level of correctness. And there's a few kind of weird things that you see in there, like you'll see that for some reason we square the output, and the idea there is that the analogy I heard was a good one, was like, imagine if you were trying to see how far off an archer was when they tried to shoot a bow at a target, and like if they're a little bit off, it's always going to be like a positive amount off, even if they're below the dot, because like a lot of this we're doing on graphs and stuff, if it's below the dot, it's still like a positive number, and then so we square the output so that it'll always be a positive number. Then we also square it so that like small errors in magnitude aren't very big numbers, but as they get bigger, they grow exponentially, so that bigger errors are corrected more. Corrected more basically than smaller errors. We also have we're going to introduce this funny little value called alpha, and it's a way of stopping over-correctness. So say like if the numbers start getting too huge, we multiply by alpha, which is like 0 point something, to reduce the size of it and avoid over-correction. So we're going to do a little gradient descent exercise. So now instead of you having to tweak the weights, we're going to write some code to make some code to do it for us. And I reinitialized the weights to 0 here. So we're starting with 0 weights. I've just redone the neural network function there. We just have this outer product function, which is just a helper function for us. We have this alpha value, and we have this iterations value, and like your task is to figure out the most efficient values for these. We have a goal, and in this case, we're only just going to work on one of the predictions. And another kind of exercise, if there's time, is to see can you do it across all the inputs instead of just one. But so right now, the way to think about this is so you saw that as you tweaked the weights, you saw they were a little bit wrong. You went back, tweaked them again, saw how wrong it was, tried to tweak a little bit more to measure it up. Well, this program does that, but the code for doing most of it is already there for you. But the idea is like to understand that it's important, like how often, how many iterations we do to try and get to the correct point. If you do too few, you won't be correct enough. If you do too many, it'll become really inefficient. And then the alpha is like how much of a magnitude do you want there to be on the error output. And basically this is just something just for you to see it and run it and just to play around with it for a minute and to read through the code. But basically just think of alpha as any number between 0 and 1, and think of iterations as any number, and try to come up with an iteration with numbers for both of those that result in a prediction that is correct. And to predict the prediction that's correct is the first expected prediction above. And then we'll talk a little bit more about the code there. The first prediction is 0.7. So like if I put an alpha of 0.001, for example, and iterations of 10, run it, and I get an output of 0.0, which is wrong. Just play around with those numbers and see if you get it to, and use the print function liberally to try and help you debug it.
Okay, so in Python, you can multiply none by a number. So you have to.
Oh, Henry, you can give it up to the left then. Sorry.
Iteration.
Like, no,
Probabilities, you might want to integrate number
3 and 4.
0.3 alpha and 4 iterations.
Yeah. You get the same thing.
Yes.
Just say that as constants now. Magic number 1. Magic number 2.
Yeah. So that's one of the best ones. Like you can see it start. The prediction was initially 0, then it was 6, then 6, 8, then 7. You start. You know, you can see it kind of big jump at first, and then the jumps get smaller. And all it's showing there is that this is kind of the optimization of your learning algorithm. It's figuring out the weights. First time it'll probably get somewhere near enough, and then it'll start to tweak as it goes. It starts to learn the proper weights in each iteration as it optimizes. This is like a super simplistic version of it, but you can imagine how how important this can be to get these optimizations correct, and to play around with the various parameters that you're going to use in your machine learning algorithm.
Okay, I got 3.
I won't bother with the updating it to do the whole, predict the whole lot, because you won't learn too much from it except how to do for loops in Python maybe. But one thing that we didn't get time to really delve into, and if we end up doing like kind of more advanced machine learning workshop, we should do it, is the backward propagation part. This is the part where you memorize, learn what you've learned, and build like a persistent model or something like that. But this is the fundamentals of it. Do you think that, from what you've seen there, that you've kind of got a very, a loose grasp on how a neural net works? I think it's called, just these basic steps that go on there. Predict, learn. So we've looked at predict, we've looked at compare, but we haven't really looked at learn so much. It's yeah.
Oh, sorry. The thing we want to get out of this is the weights, though, isn't it?
Yeah.
So just print the value of weights at the end. Is that?
Kind of, yeah, that would be one simple way to do in this scenario, for sure. Like, but there's a huge amount of kind of extra theory on the backward propagation side of things to look into, and even in these other things that we looked at, this is like the simplest possible thing I could come up with to represent how this works. So next thing is just going to be me showing you something. There's no kind of practical work to do in here, but I ripped this one straight out of the Coursera deep learning course. The CAT categorization problem is in the first module of that specialization if you ever take it, which I highly recommend. And I'm just going to play through it, and don't worry too much if you don't get every bit of it, but I'm just hoping that what we just did about neural networks will help kind of understand a little bit what we're doing here. And you're going to see a lot of mathematical notations in there, don't worry too much about that stuff. It's just to show you. What we're doing is we're going to load in training sets and test sets. So I mentioned before a training set of CATs where we have labeled data, a test set to do some verification against it. Just showing you an example of a picture. Actually, is everyone on this workbook? I'll go to logistic regression, it's called. Here's an example of one of the cats. I mentioned earlier about shape. When we talk about shape, it is the shape of your data, as in you could think of like how much data you want to get processed in each kind of go, essentially. And just printing out some of the values here, lots of stuff there, don't worry too much about it. But like what we're saying is that each image is of a certain size, we're kind of decomposing them down to their RGB values, we're flattening them out, we're letting the system know about the shape of that data that we're sending in. I just talked a little bit here about some of the matrix operations that you're going to see in there, but I won't go into detail about them right is us just massaging the data essentially, and getting it in a shape that it can be used. Jumping through it very quickly. This is a good kind of representation of a neural net. So like we had this simple Python function before. Now it's just going to be a little bit more complicated because we're using like much larger amounts of data. But essentially, it boils down to roughly the same thing. We're just using some more complicated functions with some mathematical background to like the sigmoid function there, for example. And actually what you get out is a probability, the same as what we were getting in the last problem, but we run a sigmoid function on it, which gives us a Boolean, essentially. And a logistic regression is a neural network, much like the one we did in the last one, but it's just a very simple one. It's like one neuron. I don't know why they keep using network for it, but even if it's one, but they call it that. And we're just doing the similar loop as before. Calculate the current loss, which is make the prediction, do the comparison, calculate the gradient descent, and then update the parameters, as in update weights and stuff. I mentioned before the forward propagation is the kind of prediction step. Tons of feel free to peruse this later. But it's like I tried to document as best as I could everything in there. So if you do end up looking back at it, hopefully there's enough in there to at least help a little bit to understand it. Next step is the optimize function. So again, as I mentioned, like a slightly more complex version of what we were doing before with adjusting the weights. And then the model is the bit that puts them all together. Sorry, the prediction function. The model puts them together, iterates over the data. You can see that getting printed out. You can see that as we're doing forward propagation, we're optimizing a little bit. We're coming back and we're updating the cost and coming out with predictions. And we can see that in our training set, it looks great. We got like 99% accuracy because the model is trained on that data. But then when we actually put in test data, we see that it's only getting 70% right. And that's just the whole thing, that we don't have enough data for it to be that as accurate as we want it to be. So 70% is actually pretty good considering the small amount of data that we put in. But it's an example of like how you need tons and tons of data to get an accurate model. And there's also, you'll come across the term like overfitting, where training sets can, like how you balance out like the amount of stuff you put into training sets can lead to, and how you treat your parameters can lead to something called overfitting, where it really does like care more about your training data, and when you put in new stuff, it categorizes it wrong or something like that. And you hear also about biases and stuff like that in machine learning, which kind of happen. Like a big example there nowadays is about Facebook, for example, the way that it'll always show you stuff that you've kind of seen before, and leads to this kind of bubble of bias. It's never coming up with anything new. It's always just based on the training data that it has. So it's a big problem in machine learning, is trying to put in some kind of randomness in there or something to try and get rid of those biases. And this is just another example of TensorFlow. I just put it in there just to show you, but we don't really have time to go into detail about it right now. So at this point, we should take a break, I think. And when we come back from the break, I'm going to talk a little bit about TensorFlow. And the first thing we'll do is we'll look at high-level machine learning APIs in TensorFlow. So it's kind of an easy enough going one. We're just going to look at some kind of cool things that TensorFlow has for doing machine learning. Then we'll look a little bit more. I'll show you a little bit of using like an external machine learning API just as an example. And then we'll look a bit more at just TensorFlow itself, and learn more about that library in case you want to start using it. All right, so we have 45 minutes. Get what we can. Alright, so one is TensorFlow. TensorFlow is an open source library that Google built to do machine learning stuff. It replaces a kind of an internal tool that they used to use, and they're really pushing it. And they're doing providing a lot of great stuff with it. I think I mentioned before about PyTorch is another option. There's tons of options out there. Like the way I think about TensorFlow is if you're doing JavaScript, it's like the Angular of the machine learning world. It does like a little bit of everything. Whereas PyTorch is kind of like the React. If you're familiar with what that is, it's a lot more concise and a little bit easier to use, I think.
What you're saying is one has a huge API and one has a small API.
Exactly, yeah. And TensorFlow is incredibly opinionated about how you do stuff, and so you get a lot of nice stuff with it, but you just got to play by its rules, and they can be a bit tricky to work with and hard to understand. It's a big learning curve. What is TensorFlow made of? It's got this. You can almost think of the TensorFlow distributed execution engine as like kind of like a sort of like a JVM, right? Or similar thing where you can feed it TensorFlow particular stuff, and it can run it on any hardware and whatnot. It'll run on CPUs, GPUs, Android devices, iOS devices, other stuff, Raspberry Pis. And then on top of the execution engine, this distributed execution engine is like low level, I think written mostly in C++ and C. And then they provide some front ends to interact with that, so you don't have to go in there and work at that level. You can use the Python front end, which is the most featureful and one we use generally, but you can, if you prefer, you can use any of these languages that there's support for them on top of that distributed, or basically most of them interact with, I think it's the C++ front end underneath, and then they just build on top of it. The exception of R, which I think wraps the Python front end, so it has feature parity with Python, but it's a bit weird. It's like not the recommended way to do it. And I mean, that was just some subset that I knew about it when I made that slide months ago. There's probably tons more languages out there now supported. And then on top of so that's the TensorFlow framework. On top of that, then you've got all these extra things that come with it. You've stuff for building your models. You've got Keras models and estimators, models in a box. So you can just take some model that someone else built, import that and use it, or you can build your own and export it. And I think I will show some examples of that before I move on. So here we have a high-level ML API workbook. We're going to go in there. Good. So in this one, I have this image in the assets directory in the repository. I use matplotlib to. Oh yeah, so this is where you might get hit by a downloading problem, because there's this thing downloads data.
It's coming from GitHub. That shouldn't be blocked.
96 next.
Loading in.
Someday we're going to get put in there. And so I have this image of a cat. And we take that cat image and we alter it a little bit so that we can use it in our system. We just turn it into an array essentially. And we're using something called Inception version 3. That's an estimator, a canned estimator that's provided. I think it came out of some machine learning competition or something, and they just made it public. And what it is it's an image recognition estimator. And when we run it, we've given it the image of a cat. We've put it into the pre-trained model, and it gives us a list of probabilities of what that is. So there's like a 0.97 probability it's an Egyptian cat, which is what it is. There's other probabilities in there that are not so likely. So it's kind of cool. So if you want to take a few minutes to play around with that code, and I try to put in some other image. You just download an image and point it in your file system to that image and see what predictions comes out. You can also look at the CRAS canned estimators and see is there another one that you'd want to try out. A funny one about this canned estimator is it was never trained on people. It's only been trained on objects, things, animals. So if you put a picture of yourself, it's usually pretty funny. I put a picture of myself in, and it told me there was like a 0.8 probability I was a pencil. So, coming towards our last exercise, I'd say. So when you're using TensorFlow, kind of away from all the fun machine learning stuff is the kind of boring side of it, where you've got to actually get the data into a format that TensorFlow can use. And like, this is always going to be a problem you're going to come up against, where you need to take data from whatever sources you have, usually a bunch of different sources. Usually you'll end up like, storing that data somewhere else, aggregated. You might put it in a database or whatever, but often you'll put it into files. And in big data, you often use files for this stuff. And TensorFlow has a format called TF records, which is a supported data format that it wants you to put the data into when you feed it into TensorFlow. And essentially, this is just a kind of a dictionary, and as long as you follow that format, you'll have no problems with TensorFlow. You can put almost any data in there. I just have a link in there. I'll share these slides around after, but link in there to the protobuf file for what the TF records data structure is in a class or a data structure called example, and protobuf is a kind of a data format that Google use internally. We use it in Spotify as well. It's pretty cool. It's a great way to define your data and send it around in binary format if you want. So what we're going to do now, actually, what's the next one again? Yeah, I'm going to just show you an example of using this kind of API for working with TF records. And again, don't worry too much if this isn't like totally clear, but I just wanted you to see this and kind of, so at least if you go off trying to study TensorFlow yourself later on, that it's not like totally alien, or you get some exposure to it. Because when you do go looking at the TensorFlow docs, there's so much there. It's just good to get a small bit of a head start before you're looking at it. So here all I'm doing is just importing TensorFlow, of course, and I'm setting up a graph. Setting up a session, and the best way I've found to describe those two things is to think of a graph like a blueprint for your machine learning system, and a session for like the construction site where you're putting the data in and doing all that. So the graph is like a graph of operations, and sessions where the data is. Just to show you, like right now there's no operations on that graph, it's not going to do anything. When we say TF constant there, we're actually adding an operation to the graph, and we're saying add an operation, a constant operation onto the graph that creates a constant of 4. Then when we did this thing here, we run on the session, and we like took 1 from 0. We actually created a new operation on the graph. I'm just showing you that because there's an important distinction. If you want to do something that's kind of ephemeral, where you're not altering the graph, you just want to do something to some data on the graph without changing the graph, you use this thing called feeddict, and you pass in whatever value you want to run in there. Again, don't worry too much about the specifics. It's just that you're familiar with these two different concepts, like that you're changing the blueprint or you're changing the construction of what you're currently doing with the data that you currently have. Another thing to remember with TensorFlow is that when you're passing data into it, it's actually doing data conversion in there to the data. So like it doesn't, it considers like all these data structures tensors. Does anyone know what a tensor is? A tensor is kind of a matrix with multiple dimensions. It's a thing commonly used in the kind of mathematics of machine learning, and they use it as a kind of a data type to allow you to do just all these complex operations, that are built into the library. Just to demonstrate the conversion that goes on, like there's something that isn't actually a standard Python operation that somehow works. But that's a regular Python list as far as you can tell, but in there it converts it into a matrix and does like an addition to each element in there. And just showing more examples of conversions going on. The next thing is an example of TF records. Well, here's a standard dictionary in Python. Then we have this incredibly verbose bit of Python, which is a TF record. So this is if you were building a TF record in memory, which you should probably know, you wouldn't normally do. Like you're usually reading it in from a file, but this is just to show an example of it. And this is what it looks like. If you looked in the protobuf, you'd see like you have this example, and these are the values that you can pass into it, like features. So it's an example with basically a list of features in it. So we think about, and I mentioned before, features are like your columns of data. Here I'm just creating just an image. I'm just generating an image basically, and giving it a label. I'm saying, so like the way we had the training examples of cats, for example, we had like an image and a label. So here we're just randomly named label there, number 9, and just a randomly kind of generated image in there, well, a hard-coded image. And we're going to write that to a file. So we're inserting it into the TF records. I'm going to write it to a file. And then just reading it back out from the file. And just to prove that it did come back out from the file, we can see that it has a label there. To show that there's these things, those functions that TensorFlow has are supposed to be helpful for digging around in bunches of data. And as you like if you are working with data a lot, you spend about 60%, this was from a Forbes article, but they reckon people spend about 60% of their time just cleaning and processing the data and getting it in the right shape that it can be used in a system. And they spend like very little time doing anything else. Collecting data sets is another big one. Refining algorithms like 4% of your time. The next thing that I mentioned that TensorFlow helps out with, which is, you want to get to this point where you have your question, you have your data, but you have too much data to run on your laptop. What are you going to do? You want to build a distributed computing system. And a very commonly used thing here is a MapReduce pattern, and TensorFlow supports that for you. Are you familiar with MapReduce?
So this works on Hadoop?
It can do. It doesn't have to. You can just set up any cluster. Most likely, you're going to end up using Kubernetes. Define a cluster through Kubernetes and have TensorFlow deploy on it. Has anyone not come across MapReduce before? So you. Just in case, it's probably obvious there. Like big data. Your mappers are going to just pull that data from somewhere, like break that big data down into smaller bits, do some processing on it, send the kind of process stuff onto a reducer. The reducer is going to put it somewhere else, and they kind of aggregate that data into some other thing. Like we, very often Spotify had one of the biggest Hadoop clusters in Europe, and like we just had these massive data, amounts of data put around the place. And we would say, we might want to say, for example, get the play count for a track. So you have to like aggregate all the play counts from wherever it's stored, so all the logs, Android logs, iOS logs, logs all over the shop. Aggregate them all together, put them all through all these. You could have thousands of mappers. Send that on to producers who tot up the count, and then they put that into like something like just a key value file, basically. Like you can imagine something like Redis or whatever, but it's actually a file that we use a thing called Sparky, and it loads it up into an index. And then when you have a service, then that you say, give me the play count for this track, and it reads from the index in memory that was processed that way after getting that data from everywhere else. And that's kind of an example of MapReduce.
Why do you use files to do this? Why do you use files to do this?
Because you're going to pass them, like it's not going to fit on any one machine. The data is so massive that like it's not going to fit even on a regular database. It's very hard to get all that data in there. Now Google and other big providers are getting better at creating these massively distributed databases and using things like BigQuery and all that. Spotify started moving to Google, but a lot of time it's just handier to just take the logs as they're coming in, because most of this data comes from logs. Take that log when it's coming in and just write them to files somewhere and store them in these big maps, and then build up these MapReduce jobs and then put them into databases. The example I gave there happened to throw them into a file, but they would often go into databases as well. TensorFlow supports this. There's this kind of API TF device is a method that it has, and you can define, like you can go, you're on your laptop, you can say I want this to run on one of my CPUs, or you can say I want this to run on my GPU, or you can say I want this to run on some other machine somewhere. So you can go in and like configure a full cluster of machines like this way, but usually, as I said, you would use some other tool to interact with TensorFlow, like Kubernetes, that would like generate your cluster on the fly, or in some way, like pre-configure it in some way, and the TensorFlow can read that in and use that, so you're not like actually coding in addresses and stuff. Cool. Not the end yet. I really got to remember what the slides are. I wanted to just quickly show an example of MapReduce in TensorFlow. Sorry, I meant to convert that to be white background with black text, but I didn't. But what I've done here, and this will only work unfortunately if you have like a bash set up. So if you have like git bash for Windows or something, if you're on Windows or if you're on Linux, this will work fine. But I just want to give you a demonstration of a MapReduce in TensorFlow. Each of these consoles here is mimicking a machine. So each of them have their own. It's 4 processes, and you can just pretend that it's 4 processes in a data center on 4 different machines. And in this directory here, in the machine learning workshop MapReduce TensorFlow directory, there's a couple of shell files, and they have. If you really want to, you can paste the environment variables into your Windows command console and set them in there, but it'd be a lot of hassle. But in here anyway, I can just go source, it's config, and our cluster is going to have a file server. And the problem we're trying to solve is we're going to do a word count. So we have like this big bunch of files, all just files with words in them, and we're going to set up a MapReduce job that takes all those files off a file queue that we create in the file server, and it's going to map across them, tot up the words, put that into the reducer, and come up with a sum total at the end. So the first one I'll make here is the file server. This console is becoming a file server. I'm going to source, and make this one the reducer, and then I need 2 mappers down here. 0 and 1. And I've actually only got 1 Python file in there. We'll have a look at that code in a sec, but the Python file changes what it is based on the environment variables that we just loaded up. I think it's called count.py. So starting up the file server here, I'm going to start up the mappers. And finally the reducer. reducer here, we should see all going well. I have a simulated delay in there. Like this would actually be finished in about like a fraction of a second normally. And eventually it'll just tot up. I think it's just like 1,500 words or thereabouts. Okay, so that's it. And then just to show you the code there. Count that pi. Oh, there's something. What is it? Control shift equal. Control equals. Zoom in.
Control plus, shift plus,
Control shift.
or
plus.
is it no shift on the boot?
I think I can go to view and zoom anyway. Control plus equals. That's not even, yeah, it didn't work anyway.
No shift. Strange.
Okay, and then we can hide this. I like added tons of documentation in that file, so if you're interested, yeah, we didn't obviously do a machine learning algorithm there, just a really simple word count, but you can imagine you could apply a machine learning, put your machine learning code in there. But just to keep it super simple, this was just the example. This thing here, run config, that's the thing that takes the environment variables and decides what the machine is, or what its current context is. So if we take like a file server, we loaded up this tfconfig environment variable. TensorFlow, that run config class just knows what that is. It just looks for that environment variable, and if it exists, it uses it. And we configured a cluster. And you can imagine how this cluster value could be auto-generated using something like Kubernetes or maybe even Cloud Foundry, I don't know. And we're assigning, here we're just saying localhost, setting them up, but you know, put really best is in there. And we're saying that this particular one that's loaded right now is a file server. That's all. So all these files each have the same kind of variable for the cluster, and they just have their own what they are then put in there. Yeah. And there's like an index. So if you have more than one of anything, there's an index associated with it. So this was mapper 0, mapper 1. You got mapper 2, mapper 3, etc. And this, if you're curious, this thing here is to stop TensorFlow from trying to use the CPU or GPU, because if you installed like the GPU version of TensorFlow, it could have problems if you don't have a GPU that supports it. I think you like pretty much have to have some kind of NVIDIA one. And it just comes out here and it starts up servers. I'm just going to fly through this because we have to finish. But it decides, like, it sets up a file name queue. It initializes that only on the file server, but it passes a reference to that to all things in the cluster. Similar, it creates like mappers, reducers, but it passes the references around and handles the communication between them for you, so you don't have to worry about that stuff. So it's like you can have all your code in one file, and yet it's running on an entire cluster. So it's pretty cool. And then in the end, it just maps, does a word count, sends it to the reducer tots up the total, and outputs the total in the end. And that's that. And that is it. That's the end.